that, before we learn how to separate the excited state electron with holes, the first question will be, what material is used to absorb light? Remind me that I still have 9 more minutes. Kalau dah 10.50 cakap. Sorry, 11.50. What material is used to absorb light? Next. Straightforward, we need semiconductor. But why? I will explain why. So we need semiconductor for photovoltaic device. This is device structure. Let's say we have semiconductor A. We have valence band, the red one, and we have conduction band, the blue one. And if we expose material A to the sunlight, what will happen? Next. 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 Okay, back. Alright. We have learned this just now. If we expose the semiconductor to the sunlight, what will happen? If the sunlight with sufficient energy, it generates excited state electron. This is hole. This is excited state electron. So in the excited state electron, and if the excited state electron and hole could be separated, electron flow could be initiated. We have discussed that. Producing a voltage and a current in an external circuit. So next. This is how we separate the excited state electron and hole. By pairing semiconductor A with the next semiconductor, which is semiconductor B. But there is a requirement. The conduction band of material B should be at lower energy than the conduction band of material A. And the valence band of material B should be lower than the valence band of material A. This is the requirement. We need to separate the electron from hole. We don't want this electron to combine with hole. So this is how we do. Pair up another semiconductor that has conduction band lower than material A. So what will happen if we pair them up? Remember this? Electron sinks, hole float. Electron sinks, hole float. Electron sinks, electron tenggelam, hole floats. So what will happen now is this conduction band, the conduction band of material B, provides a location for this excited state electron from material A to be injected. So this electron sinks to the lower energy band. Of course, this one is lower also, this one is lower, but this electron will prefer to be injected to the nearest lowest energy state. So this is the nearest lower energy state, not this one, this is further. So this electron prefers to be injected to material B. How about electron? Electron floats. Can it float to this one? This is sink. This is sinking. So it cannot float, it stays there. This one stays there, sterics. This electron could be injected to conduction band of material B. So we have separated this hole with this electron. Then we continue with other component, for example, conductor, to extract this electron out from the solar panel. So basically we have material A, material B, we make PN junction. Double jalan semikon PN junction. We will revise PN junction in this course. Next. So the excited state electron loses its excess energy by Foster resonance energy transfer. So this electron injection, electron from high energy state injected to the low energy state, known as FRET, Foster resonance energy transfer. And of course, the electron will lose its energy a little bit. How much does it lose? The difference between the conduction band and this conduction band will be the energy loss. It goes from high energy state to the low energy state, it will lose some energy, but still energetic. Still, the electron is useful to be mobile and creates electricity. So the next jargon is FRET, Foster resonance energy transfer. Next. Okay, I already gave to you the hints: electron sinks, hole floats. Next. Okay, so this is how the injection happened. The electron could be diffused to the edges of material A, then injected to the material B. See the difference of energy. This has higher energy, this one is lower energy. Of course, there will be energy loss. Energy loss could be in the form of heat, in the form of electronic vibration, electronic translation. So during the movement from here to there, the energy will be lost as kinetic energy. Next. So, if we able to channel out, to install external circuit, and of course we could extract the electron out and create electricity. Whenever the electron could be moved, of course we got electricity. Next. So this one will be the last slide for today's class. We only still have 5 more minutes. Let us see what is Foster resonance energy transfer. It's a mechanism describing energy transfer between two light sensitive materials. Whenever the electron is injected, it is FRET. Injected from one component of the semiconductor to the other component of the semiconductor, it's known as FRET. So one material has higher conduction band, which is known as donor of electron. For example, our material A, it has higher conduction band than material B. So material A is an electron donor. Then the other material is semiconductor B, which has lower conduction band. It is known as acceptor of electron. So the efficiency of this energy transfer, the electron injection, how efficient the electron injection after it is being excited. We have atom A, okay, all of electron in the ground state could be excited to the conduction band. Now the next question is, this electron needs to be injected to semiconductor B. Question is, how efficient all of the electron being injected to semiconductor B? If we have 100 electrons could be generated in semiconductor A, but somehow if we only could manage to inject only one to semiconductor B, will our device be efficient? If we could produce 100, we need to extract 100 to be injected to semiconductor B. And we could calculate that electron injection using our instrument. We have instrument over here. We have the photoluminescence. So the efficiency of that electron injection is inversely proportional to the 6th power of the offset. What is offset? The difference between energy level of donor and acceptor. The energy difference between the conduction band of material A and conduction band of material B. That is the offset. So, if our offset is big, will the FRET be efficient? If the offset of our system is big, let's say, let me draw. We have system A and we have system B. Conduction band, valence band of material 1. We have conduction band and valence band of material 2. And the offset is, let's say, for example, the offset is 0.1 electron volts. And we have system B, conduction band, valence band, material 3, and conduction band, valence band of material 4. And the offset is, for example, 0.5 electron volts. So which system that you predict will give you high efficiency of FRET? System A or system B?
A.
Guys? A? A? A. Correct. System A will give you more efficient threads, more efficient electron transfer from the conduction band of material 1 to conduction band of material 2. So this is one of the factors how to choose material. We need to make sure that the offset between the neighboring material is at minimum to prevent from low efficiency of the thread. So I think that's all for today. You have learned too many jargons today. Any question? No? Amin? Tak nak tanya corrosion. Okay, Farah, again. Mana Daniel? Oh, terseruk. Okay, any question? Right. Girls, back there? Right. We will have quiz next week about these things. Okay? Right, prepare.